So in this exercise, we have to find the steady state values of the capital stock, output, and consumption in per worker terms in steady state. Before finding the steady state values, we always said there's one single step that we have to go through before starting, and that is to compute the per capita production function. In this exercise, luckily, the per capita production function is given, so we do not have to spend any additional time on finding an expression for the per capita production function. So we can just start by finding. So before before finding the steady state values of both consumption and output in per worker terms, we first have to find the capital stock in per worker terms in steady state. And how do we do that? Well, we recall that the capital stock in period t plus 1 is equal to the capital stock in period t plus investments minus depreciation of capital. In steady state, we know that, so in steady state, we impose the steady state condition, and that is that the amount of capital that we have in period t plus 1 is equal to the amount of capital that we had in period t. In other words, the change in the capital stock in steady state is equal to 0. And we also drop the time subscripts. Why? Because the timing doesn't matter. The capital stock is the same in period t as in period t plus 1. Therefore, we do not want to distinguish between the time. Okay? So we do not care about the timing when we're in steady state. Therefore, we have that k should be equal to k plus investments minus depreciation of capital. K cancels out, and we get that 0 should be equal to investments minus depreciation of capital. So what we can do now is we can rearrange this expression. We add the depreciation of capital on both the left and right hand side, and we get that delta k should be equal to investments. So remember one thing, we are in a closed economy, and that means that savings are equal to investments. So instead of writing y, I could also write savings rate times total output. So remember, y denotes my total income and s denotes the savings rate. It tells me how much I choose to save out of my total income. And since we're in a closed economy, we have that savings is the same as investments. So what we have now is that we end up with the following equation. Delta k should be equal to the savings rate times total output. Now what we want to do is that we want to transform this equation, let's call it star equation. We want to transform this equation in per worker terms. Transform to per worker terms. How do you do that? Well, we divide by n on both the left hand side and the right hand side. Now what we have on the right hand side is the output per worker, and this function was given initially in the exercise. So we replace y over n with the exact functional form, that is k over n to the power of 1/3. So I write delta times k over n should be equal to the savings rate times k over n to the power of 1/3. What I can do now, so what do we want to do? Well, first we have to solve for the capital stock in steady state in per worker terms. So we have to solve for k over n. So I start by dividing. I divide by delta on both the left and right hand side. And then we divide by k over n to the power of 1/3 on both the left hand side and the right hand side. And then we know that this here can be simplified. This is the same as k over n to the power of 1 minus 1/3 saving rate over delta. So we have that the capital stock per worker to the power of 2/3 should be equal to the saving rate over the depreciation rate. Now we need to solve for the capital stock in per worker terms in steady state. How do you do that? We raise both the left and right hand side to the power of the inverse that the capital stock in per worker terms in steady state is raised to. That is 1/2, 1/2. Then we get that k over n raised to 2/3 times 3 over 2 should be equal to the saving rate over the depreciation rate, everything raised to 1/2. We have a times 2 and divided by 2, that is just a 1. And we have a times 3 divided by 3, this here is all just a 1. So the capital stock in steady state in per worker terms is equal to the saving rate over the depreciation rate raised to the power of 1/2. Now once we have now we have the capital stock in steady state in per worker terms, we can easily compute the output in steady state in per worker terms and the consumption in steady state in per worker terms. So the output in steady state in per worker terms is equal to the capital stock in steady state in per worker terms to the power of 1/3. So I plug in the exact value of the capital stock in steady state in per worker terms. That is what we just got right here. And then we get that the output in steady state in per worker terms is equal to the saving rate over delta to the power of 1/2, everything raised to 1/3. This we can simplify, so the output in steady state in per worker terms is equal to the saving rate over delta to the power of 1/2. Remember what I said before, so we are in a closed economy. And whenever we're in a closed economy, we know that savings. So we know that savings are equal to investments. Yeah. And we know that the total output must be equal to the sum of consumption and savings, total savings. So if we want to find the consumption level, we simply solve for C. So total consumption, so consumption must be equal to total income minus your savings. And savings I can rewrite to the savings rate times total output. So total consumption must be equal to your income minus what you save. This is just y times 1 minus s. This is just a way of rewriting it. And since we need to know what the consumption level is in steady state in per worker terms, we need to transform the whole equation to per worker terms. So just divide by n on both the left and right hand side. Since we need the consumption level in steady state, we need to plug in the output level in steady state in order to find what the consumption level is. So consumption in steady state in per worker terms must be the output in steady state in per worker terms, that is the savings rate over the depreciation rate to the power of 1/2 times 1 minus the savings rate. So in this exercise, we have to find the level of capital per worker in the next period. So in period T, or say in the current period, we know that the capital per worker is equal to 4. So in order to find the capital per worker in the next period, that is in period T plus 1, we need to write up the capital formation equation, and we have to rewrite it in per worker terms, since we have to find the level of capital stock in per worker terms in period T plus 1. So what do? We insert the values. Capital per worker initially, that is 4. It's given in the exercise. Here we have it again, KT over N, that is the initial capital stock in per worker terms, that is 4. And then we have the output in per worker terms, which is unknown, but since we know that the capital stock in per worker terms initially is equal to 4, we just plug in the 4 into our output per worker function. So we get 4 raised to 1/3. Okay, and that is the way that we solve this one. So you take 4 and you raise it to 1/3, and you get that the output in per worker terms is equal to 1.58. So now we know that the output in per worker terms is equal to 1.58. The saving rate we also know that is 0.3. The depreciation rate we also know that is 0.1. So the level of capital per worker in period T plus 1 must be equal to 4 plus 0.3 times 1.58 minus 0.1, that is the depreciation rate, times 4. And if we calculate this, we get that the level of capital per worker in the next period is equal to 4.0. So in steady state, so we have computed the capital stock in steady state in per worker terms. That is the savings rate over the depreciation rate raised to 1/2. This value we can compute by plugging in the saving rate and the depreciation rate. And if we do so, we get that the capital stock in steady state in per worker terms is equal to 5.2. Now, in question 3, we're asked, will the capital stock increase or decrease in this economy over time? Will output increase or decrease over time? So, since in question 2, the capital stock in the previous question was equal to 4, since 4 is below the steady state value, we will have that total investments in per worker terms will exceed the depreciation of capital. That means that we will accumulate a higher stock of capital in per worker terms. As a result, output will increase over time. So whenever the capital stock in per worker terms is below the steady state value of the capital stock in per worker terms, we'll have that investments will exceed the depreciation rate, and as a result, the stock of capital will increase in the economy, and therefore output will also. So in question 4, we have to find the golden rule value of the savings rate. Remember, the golden rule value of the savings rate is that savings rate that maximizes consumption in steady state. In order to find this savings rate, we need to differentiate the consumption equation that we found earlier in steady state with respect to the savings rate. So we write up the consumption equation that we found earlier. that is a function of the depreciation rate here and the savings rate right here. So in order to find the golden rule savings rate, I would like to rewrite this equation. This is the same as the savings rate over the depreciation rate raised to 1/2 minus the savings rate times the savings rate over the depreciation rate raised to 1/2. Now we will take the exponent here and plug it in here and here, and we'll take the exponent here and plug it in here and here to simplify our differentiation part. So consumption in steady state is equal to the savings rate to the power of 1/2 over the depreciation rate to the power of 1/2 minus the savings rate times the savings rate raised to 1/2 times 1 over delta raised to 1/2. I can also drag down the savings rate here in front of the fraction. So we can write s to the power of 1/2 times 1 over delta to the power of 1/2 minus s times s to the power of 1/2. That must be equal to s to the power of 1.5 3/2 times 1 over delta to the power of 1/2. Now what we do is that we cannot write this expression more explicit than we did right now. So we take this and differentiate it. So we take the consumption in steady state in per worker terms, and we differentiate it with respect to the savings rate and set it equal to 0 because we want to find that savings rate that maximizes the consumption in steady state in per worker terms. So differentiating this first part, we take down the exponent, that is 1/2 times s, and we subtract 1. And then we have 1 over delta to the power of 1/2. That is just a constant. It remains. And then we're missing the last part here. S to the power of 3/2, we take down the exponent, multiply by s, and we subtract 1, and then we get 1/2 times the constant, 1 over delta to the power of 1/2, and we set everything equal to 0 because we're maximizing. Now we multiply by delta to the power of 1/2 of both the left hand side and the right hand side. If we do so, we'll get that this cancels out with this here, and this here, and this here is simply a 0. So what we're left with is 1/2 times the saving rate to the power of minus 1/2 minus 1.5 times s to the power of 1/2. And everything should be equal to 0. So what can we do now? Now we can multiply by 2 on both the left hand side and the right hand side. If we do so, the 2 will cancel out with 2 here and the 2 here. So we're left with the savings rate raised to minus 1/2 minus 3 times the savings rate raised to 1/2. This should be equal to 0, remember. So here we have 0 times 2, which is just a 0. Rearranging, remember we want to solve for the savings rate. Now the savings rate that we find here when we solve is that savings rate that maximizes consumption in steady state. Rearranging, we get savings rate minus to the power of minus 1/2 should be equal to 3 times the savings rate to the power of 1/2. what do we do now? Well, we can multiply by the savings rate to the power of 1/2 on both the left hand side and the right hand side. If we do so, on the left hand side we get s raised to 1/2 minus 1/2 should be equal to 3 times s raised to 1/2 plus 1/2. This here is a 0, so we have on the left hand side we have s raised to 0, and then on the right hand side we have 3 times the savings rate raised to 1. S to the power of 0 is just equal to 1. On the right hand side we have 3s, so the golden rule savings rate must be equal to 1/3. In other words, if the savings rate is equal to 1/3, consumption is maximized. So exercise 2, question 5 and 6 combined. So in exercise 2 we have that the saving rate is equal to 0.3, and now we're asked to assess the effect of an increase of the savings rate on steady state consumption. Steady state consumption, right? Remember, the golden rule savings rate, that is the savings rate that maximizes consumption in steady state. So initially, so here is the consumption level in steady state if the savings rate is equal to the golden rule savings rate. So right now we have that the savings rate is equal to 0.3. That is to the left of the golden rule savings rate, because we found earlier that the savings rate that maximizes consumption in steady state is 1/3. Since we are to the left of the golden rule savings rate, we are at 0.3. It must be the case that if we increase the savings rate, consumption in steady state will increase. Similarly, if the savings rate is equal to, say, 1/2, 0.5, we will have that an increase in the savings rate from 0.5, let's say we go to 0.7, will decrease consumption in steady state. So if the savings rate is below the golden rule savings rate and we start increasing the savings rate, consumption in steady state will increase. If the savings rate in the economy is larger than the golden rule savings rate, then if we increase the savings rate, consumption in steady state will decrease. And again, here consumption in steady state will increase.